In recent years, AutoML has gained in both popularity and effectiveness. As a part of the Advanced Research and Software Engineering team at NDSU, I am developing a new approach that also takes fewer resources. Our initial results look very promising, as we can consistently predict effective hyperparameters using far fewer resources compared to existing approaches. These results are achieved through the software engineering concept of sketching. For the purposes of this presentation, a sketch is simply a partial machine learning program, where the high-level framework is in place, but the details need to be filled in, kind of like an abstract class in object-oriented programming. We use an artificial neural network to predict how to best complete the partial program or sketch. The artificial neural network is trained on meta features extracted from the dataset. Let's take a closer look at how AutoML works and why my approach is novel and effective. AutoML, which is an abbreviation for automatic machine learning, is a technique used by those with and without a background in computer and data science. The appeal to AutoML is a user doesn't have to design the model or choose the hyperparameters of an existing model. Instead, the user simply provides the data and the AutoML program generates a model from the data. Existing approaches use an optimization technique to generate models. The generated models are trained and the user can pick the most accurate. Another existing approach is to continually train a model. If there is an improvement, we go to the next generation. Both these approaches are slow and can take many hours to complete. My approach differs because it does not iteratively train many models, which can take a long time. Instead, my approach uses an artificial neural network that predicts how well a parameter will do on the data. We can generate a prediction for how accurate certain parameters will be much faster than training a model from scratch. Here are my key observations of this approach. The key observations from this experiment is that data sets with similar meta features tend to use similar machine learning model parameters. Meta features can be categorized into different sets. General, which is the data type of the columns. It also includes what column to predict. And statistical, which are the statistics of each column. The same model is generally effective at predicting data from different data sets with similar meta features. This in turn will greatly decrease the search space of the parameters. In this approach, we trained an artificial neural network on the meta features from many data sets. The artificial neural network is very effective at predicting the parameters for unseen data sets. Here's a high-level view of how this approach works. The user creates and submits a query, just like any other AutoML program. But in our approach, the query is parameterized and a partial sketch is created. A partial sketch contains data, such as the data types of each column and what column to predict. To complete the partial sketch, next meta features from the data are calculated, such as whether a column is categorical or numeric, along with the statistical features of each column. Then, the data is sent to an artificial neural network in the trained model sector. It predicts the top K models that are most likely to perform well on the data and sorts them from best to worst. The hyperparameters are identified from the top models and used to fill in the holes of the partial sketch. The sketch is now complete and is verified by training it on the data. The model is returned to the user who now has a complete machine learning solution. The implementation of this framework can be divided into 4 phases. Firstly, we collected 450 classification datasets, which make up an exhaustive model search space. The datasets came from OpenML and include, but are not limited to, several domains such as medicine, industry, finance, social science, and others. The second phase was devoted to the meta feature extractor built in Java. Next, the modules completed in the preceding phases were used to construct the meta learning model sector. The phase involved creating models for each algorithm in Python using keras. All meta-learning models were combined in a wrapper to build a ranking generator across the entire search space. Lastly, Python templates for the operations of the machine learning pipeline were written. These are used by the partial sketch synthesizer and the sketch completion program. This is an example of what a user query would look like using our approach. In this example, a hydrologist would like to predict the average water level of 3 wells based on their historical water levels. Our query is being compared to an existing solution using AutoSKLearn. This is to show that the syntax of our approach is similar to other popular AutoML approaches, in this case AutoSKLearn. Each step of our query syntax can be mapped to this chart in the previous slide. Initiate the dataset, initiate the model, which will create the partial sketch. In this case, the partial sketch will contain 3 numeric columns: precipitation, humidity, and wind speed, along with a 4th numeric column, which is the column we want to predict, the average water level of the 3 wells. Train the model using the best hyperparameters found in the search space, and finally, return the machine learning solution to the wells model pointer. This table shows the accuracy result of our approach. Please note this is not the prediction accuracy of the synthesized models. This is how effective the artificial neural network is at predicting the best parameters for a given dataset. We judge our accuracy by comparing the top-ranked K predicted parameter sets to the best known parameters within an error range of R for a given dataset. K is the top predicted models. So the top 5 best models, top 10, top 15, top 20. R is the error range from the best known parameters that the predicted parameters must be within to be considered an effective solution. R is 1%, 2%, and 3%. Take column 5 for example. This is the percent accuracy. There were a set of parameters from the top 5 predicted models that match the best known parameters from that dataset within an error range of R. More specifically, in the logistical regression category, 84.88% of the time, there was at least one predicted model among the top 5 whose parameters were within 2% of the best known parameters. The second table provides a timing comparison in seconds of my approach to other AutoML approaches. My approach takes considerably less time than other approaches. This is because we are predicting hyperparameters and only training the model once, instead of using an optimization technique that iteratively trains many models. This is where my approach really stands out. Our approach translates a user query to an appropriate machine learning sketch, completes the sketch using a neural network that predicts the best hyperparameters for the sketch. It then verifies it on the user data and returns the complete machine learning solution. On popular datasets, we consistently predicted the best known parameters while outperforming other popular AutoML approaches on wall clock time.